line graphs and edge coloring. Recap of previous lecture, we have discussed the elementary properties of subdivision and minor of a graph, Kuratowski's theorem, Wagner's theorem, and also proved non-planarity of Peterson graph. Content of this lecture, we will discuss the line graphs and how the line graphs are used in edge coloring and one factorization of a graph. So, let us see the concept of line graph and we will use it for the edge coloring. So, many questions about the vertices have analogies for the edges. Independent sets have no adjacent vertices and matchings have no adjacent edges. So, analogs with vertices and corresponding problem in the edges are also there with a different name. If no vertices which are adjacent called independent sets, then for the matching no edges are adjacent. Now, vertex coloring partitions the vertices into independent sets. We can instead partition the edges also into the matchings. So, these problems we can relate via the line graphs. Here we repeat the definition, emphasizing our return to the context in which the graphs may have the multiple edges. We use line graphs because the edge graph is not a proper term. Now, let us see the line graph. Line graph of a graph G is represented as L of G, is a simple graph whose vertices are the edges of that graph G, with the edges of line graph is nothing but when the edges of G they are meeting at a common point. Take this particular example. If this is the graph G where we have labeled the edges with their names. So, for every edge there will be a vertex in the line graph. Now, as far as the edge in a line graph says that whenever these two edges in the original graph are meeting, for example D and E they meet, so they will form an edge in the line graph. Similarly, D and F they meet, so D and F has an edge. Similarly, E and F meets, so E and F has an edge. Similarly, D and G they meet, so D and G they have an edge, and F and H they meet, so F and H they have an edge. So, H and G they meet, so H and G they have an edge, and F and G they also meet, so F and G they have an edge. So, if we are given a graph G, we can obtain a line graph of that particular graph using this concept. So, again we can take another example. In this example we are given a graph. So, for A we have a vertex, B we have a vertex, for E we have a vertex, for C we have a vertex, and for D we have a vertex. Now, A and B they are meeting, A and B they are meeting, so we place an edge. A and E they are meeting, we place an edge. A and C they are meeting, we place an edge. Then B and D they are meeting, B and C they are meeting, so we place an edge. B and D they are meeting, we place an edge. Now, C and D they are meeting, so we place an edge. Similarly, E and C they are meeting, so we place an edge. So, this is called a line graph of this particular graph. Now, the edge coloring problem arises when the objects being scheduled are the pairs of the underlying elements. So, example of edge colorings of let us say K2n. So, K2n when n is let us say 2, so this becomes K2n graph. Now, we want a pair of objects to be considered as far as the scheduling of a game is concerned, then it requires an edge coloring, not the vertex coloring. So, in the league of 2n teams, we want to schedule the game so that each pair of teams play a game, but each team plays at most once in a week. So, since each team must play 2n minus 1 others, the season lasts at 2n minus 1 week. So, the games of each week must form a matching. We can schedule the season in 2n minus 1 weeks if and only if we can partition these edges into 2n minus 1 matchings. Since k2n is 2n minus 1 regular, there must be a perfect matching. So, we can see here that having arranged the bipartite graph, instead of that let us add, so this becomes k2n graph. So, k2n graph means if we take a particular team, so how many, because it is 2n minus 1 regular graph, so it can have a pairing with all n minus 1 vertices. So, these edges will pair. Similarly, the other edges will also have such pairings. So, different pairings are basically possible. So, we can partition these set of edges into 2n minus 1 different matchings, and how to obtain these matchings, that is the pairings, is called an edge basically coloring. So, when we obtain a pairing, so there is a rule that if these two are selected, then the remaining pair, that means this is one set of match when 1, 2, 3, 4. When 1 and 3 is one such of matching and 2 and 4 is one matching. Second matching we can obtain as 1, 4 and 2, 3 is another matching. Similarly, we can have another matching like 1, 2 and 3, 4. So, this particular graph has 2n minus 3 different matchings, and this will require 2n minus 1. So, 2n minus 1 matchings. So, here 2n minus 1 comes out to be 3. So, 3 matchings we have obtained. So, for that you might have seen that the graph has to be a 2n minus 1 regular and it has a perfect matching, then only 2n minus 1 different matchings are possible. Therefore, let us see the definition. A k edge coloring of a graph is the labeling of the edges with the color set S, where the cardinality of S is k. So, that means applying k different colors, we are placing the colors on these edges, and k edge coloring is nothing but that particular labeling or a function. So, the labels are the colors, the edges of one color will form the color class. So, k edge coloring is proper if the incident edges have different labels, that is if each color class is a matching. So, let us understand what is the proper coloring if the incident edges have different labels. So, take this particular graph. So, the incident edge on this particular vertex, if this is having label let us say red, so the other edge will have another label. Why? Because the incident edges should have the different labels for a proper. So, it is a proper two colorings, two edge coloring. So, a graph is k edge colorable if it has a proper k edge colorings. The edge chromatic, that is chi prime g of a loopless graph is the least value of k such that the graph is k edge colorable. Example of edge coloring a complete graph is basically shown over here. Now we call the edge chromatic number also as the chromatic index. So chi prime g is called chromatic index since the edges sharing a vertex need different colors. Therefore, this bound on the edge chromatic number, that is chi prime g, is at least the maximum degree of a particular graph. Wising and Gupta independently proved that delta g plus 1 color suffice when the graph is simple. So we will see that what are the conditions when the edge chromatic number of a graph, that is chi prime g, is at least delta, and what are the conditions as far as Wising and Gupta theorem that this particular chromatic index will become delta g plus 1. Now a clique in the line graph is the set of pairwise intersecting edges of G, because the vertices are representing the edges of graph G. So if there is a clique in line graph, this means that there is a set of pairwise intersecting edges of a graph. When G is simple, such edges form the star or a triangle in particular G. For the hereditary class of line graph of a simple graph, Wising theorem states that chi prime h is less than or equal to omega h plus 1. Thus the line graphs are almost perfect. In contrast to chi g, multiple edges greatly affect the chi prime g, that is chromatic index. So a graph with a loop has no proper edge coloring. So that is an important point to be noted. Hence the loopless will be excluded here, but multiple edges are allowed in the edge coloring. So multiplicity, multiple edges means between two vertices multiple edges can be there, and how many edges are there, that is called multiplicity. So in a graph G with multiple edges, we say a vertex pair xy is an edge of multiplicity m if there are m different edges with the endpoints x and y. So here let us say that there are m. So hence the multiplicity of m will be there. Now we write mu of xy for multiplicity of a pair, and we write down mu g for the maximum of the edge multiplicities in the graph. So this kind of structure where multiplicity of a graph or multiplicity of the pairs are allowed, and this is called a fat triangle. Now there is a theorem which is given by Koenig, which states that if the graph G is bipartite, then chi prime G is equal to delta G. So let us see the proof. Corollary, which is stated in the previous videos, 3.1.13 states that is the Hall's theorem, states that every regular bipartite graph H has one factor. So it's a Hall's theorem about matching. So one factor is nothing but a matching. So every regular bipartite graph H has one factor. So by induction on big delta of H, this yields a proper delta H edge colorings. It therefore suffices to show that every bipartite graph G with a maximum degree k, there is a k regular bipartite graph containing G. To construct such a graph, we add the vertices to a smaller partite set of G if necessary to equalize the sizes. If the resulting graph G prime is not regular, then each partite set has vertices less than that degree k at that edge and thus make it as k regular. For a regular graph G, the proper edge coloring with big delta G colors is equivalent to decomposition into one factor. Let us see through an example. So, let us say that this is the graph which is given, a bipartite graph. Now, here one vertex is missing, we can add that vertex to a smaller partite set. This is a smaller partite set, we have added one vertex to equalize the sizes. Now, if this particular G prime is not regular, then we will place an edge, these edges are added extra and hence this becomes too regular, or let us say it is a k regular graph. Now, having obtained, that means given any such partite graph, we can obtain a k regular graph by these set of operations, by adding vertices and by adding edges. Having done that, now you know that the big delta G of this particular graph is 2. So, we can obtain an edge coloring with at most big delta G colors. So, let us say that if this edge we color, then we cannot color the other edge which are incident on these vertices with the same color. So, the other two vertices which need to be colored, the other two vertices will require the same color which are not same. Now, the remaining edges require another color. So, hence we are using a green color. So, the remaining edges we can apply the green color. So, every vertex which is incident having the edges of different colors, how many colors, that is big delta G, the colors will be required. Let us read again. So, corollary 3.1.3 states that every regular bipartite graph has one factor. So, that is basically the perfect matching if the graph is a regular bipartite graph. Now, by the induction on big delta of this particular graph, this yields a proper delta H edge colorings. So, we have shown that, and we have also shown through this particular steps that if the graph is not k regular, we can obtain it by adding the vertices or adding an edges. So, hence this conic, we have seen the theorem that if graph G is bipartite, then chi prime G is equal to big delta G, that is for bipartite graphs. So, for bipartite graph, this particular bound holds according to the conic theorem. Let us see one factorization is nothing but the matchings, the decomposition of a regular graph into one factor is the one factorization of a graph G. So, graph with one factorization is called one factorable. So, an odd cycle is not one factorable. So, take an odd cycle, this is C5. So, an odd cycle, it is not one factorable. Why? Because if you can select this edge, then this edge cannot be selected, this edge if it is selected, this vertex will be unsaturated. Hence, this is not the perfect matching, hence it is not one factorable. Similarly, if an even cycle we can take, so we can factorize, we can obtain the one factor in the following way. So, these are all called one factors of this particular graph, 1, 2, 3, 4. There is another one factor you can obtain between 1, 3 and 2, 4. So, this is one factorable. So, the Peterson graph also requires an extra color but only one extra color. That is important point to note. So that means the Peterson graph is 3 regular, but it requires how many colors? Chi prime of Peterson is equal to 4. That means it requires big delta G is equal to 3 plus 1 more. So Peterson graph is an example where chi prime G becomes plus 1. So Peterson graph is 4 edge chromatic. So Peterson graph is 3 regular, 3 edge colorability requires 1 factorization. Deleting a perfect matching leaves 2 factors. All components are cycle. Here we can see if we delete it, this is a perfect matching. So we will obtain 2 different cycles, which I will show you through. This is one cycle C5 and this is another cycle. So 2 cycles, 2 C5 cycles we will obtain. All component cycles, the 1 factorization can be completed only if these are all even cycles. Thus it suffices to show that every 2 factor is isomorphic to 2 C5. So here we have seen that consider the drawings of 2 C5 and a matching the cross edges between them. We consider the cases by a number of cross edges are used. So every cycle uses an even number of cross edges. So a 2 factor H has an even number m of cross edges. If m is equal to 0, then H is equal to H is equal to 2C5. Now when m is equal to 2, so here we can see that this is 1 and 2. Then the 2 cross edges have non-adjacent endpoints on the inner circle or the outer circle. On the cycle where their endpoints are non-adjacent, the remaining 3 vertices force all 5 edges of that cycle into H, which violates the 2 factor requirement. So when m is equal to 4, 1, 2, 3, 4, then the cycle edges forced into H by unused cross edge form a 2 P's. This is one P and this is another P, whose only completion to 2 factor in H is 2 C's. Note that since C5 has 3 edge colorable, the graph is 4 edge colorable. Wissing's theorem, Wissing and Gupta has given a theorem which says that if G is a simple graph, then chi prime G is less than or equal to big delta G plus 1. Big delta G means the max degree of particular graph plus 1. Now if we correlate with the previous discussion, that we have seen that bipartite graph is having chi prime G equal to big delta, that also is included into it. So with this we include the definition, a simple graph G is class 1 if chi prime G is equal to big delta. It is called class 2 if chi prime G is equal to big delta G plus 1. So the example here is a bipartite graph by Koenig's theorem. We have seen this, and this becomes valid for a Peterson graph. Hence the bipartite graph is class 1 graph and Peterson graph is class 2 graph. Determining whether a graph is class 1 or class 2 is generally hard. Thus, we seek the conditions that forbid or guarantees big delta G edge colorability. So, conclusion: in this lecture we have discussed the characterization of a line graphs, edge colorings, chromatic index, multiplicity and one factorization. Thank you.